Unit 6, Part 3, we've started talking about logical implication and logical equivalence. They apply, in the first instance, to pairs of statement forms, okay? It's a relation between statement forms that does or does not hold, right? Two statement forms are logically equivalent or not logically equivalent. One statement form does logically imply another statement form, or it does not, okay? So first thing, they apply to pairs of statements. It's a relation between statements. Okay, so what is the truth table understanding of these concepts? Logical equivalence is the easier concept, so we'll start with that. We've talked about it, we've already come across it quite a bit, especially if you think back to our discussion of paraphrase, right, when we were distinguishing simple from compound sentences, right? Remember, we said a sentence like Dan and Uchenna are married. Is it simple or compound? That turned out to be simple because if we tried to paraphrase that as Dan is married and Uchenna is married, that was not a successful paraphrase because there is a world in which the second statement is true and the first statement is false, right? When Dan is married to Sally and Uchenna is married to John, right? Then it's true that Dan is married and Uchenna is married. It's not true that Dan and Uchenna are married because that means they're married to each other. Okay, so that was the idea of paraphrase. We said that was not a successful paraphrase because those notions are not logically equivalent. Logical equivalence, understood now in terms of truth tables, is just the columns under the major operators for these two statement forms are identical. Simple as that, right? Which is exactly what you expect for logical equivalence, right? True in the same world, false in the same world. Whenever the first is true, the second is true. Whenever one is false, the other one is false, right? Their truth and falsity stands in both statement forms stand and fall together. They're both true together, they're both false together, whatever. Right, so the image is just, right, this will be an example of it. You know, anytime the two columns are identical, they are logically equivalent. But right, if this is true, true, false, true, right, I always have the image is 4, but of course it can be 2 rows or 8 rows or 16 rows, but usually it's 4. If they're both if one is logically equivalent to 2, statement 1, statement 2, then this is also true, true, false, true, okay? That's logical equivalence. So the kind of question you'll get, let's work out this one. This is 3A from the exercises. Okay, test these two statement forms to see if they are or are not logically equivalent. Can do, okay, so you write them up. Not, what is this? Make sure you can read these, that you can say what these say, right? This is a negated conjunction. This is not P and Q, right? It's the negation of conjunction. So what does it say? It says not both P and Q. And the second one is what? What is the major operator here? What is this thing? It is a disjunction, right? It's the disjunction. It says either not P or not Q, right? Either not P or not Q. Notice what I say first. I say either or because the major operator, right, the overall form is disjunction. It's either this or that. Either not P or not Q. You're very far behind if you think this might be a negation because it starts with a negation. No. It only negates P, and we negated P before we disjoined these. So is not both P and Q equivalent to either not P or not Q? How do I test it? Okay, so go along and count my sentential variables. I've got a P, I've got a Q, I've got a P, I've got a Q, I've got only 2. What am I doing now? I'm going to construct a joint truth table, right? A truth table with the same base columns used to calculate the truth values of these. I should point out while I remember, as Klenk states, two statement forms can be logically equivalent even when they have a different number of sentential variables, right? One statement form with only P and Q as sentential variables can be equivalent to a statement form with P and Q and R as sentential variables, right? What you would do is you would to discern that, prove that, you would build a joint truth table with 8 columns, because you need P, Q, and R to calculate the truth values of the statement form with P and Q and R in it. You can still fill out every row for the one with P and Q. It's just that the R value will not come into the computation for that statement form, right? But every row is still determined by the values of the P and the Q. And then if the columns under the major operator, those 8-row columns under the major operator, are identical for the 2 statement forms, they are logically equivalent, right? So it's not true that a statement form with 2 sentential variables can only be given a truth table with 4 rows. You can give it a statement form, you could have a 16-row truth table column, and you could still do the truth table for, say, P, or P and Q, or whatever, right? Okay, so here we'll do the joint truth table, P and Q, P and Q. Okay, what do I do when I do base columns? I start with the rightmost, right? I list them alphabetically, start with the rightmost, and I alternate true, false, true, false, true, false, true, false. I move to the left and I double the amount of T's and F's. So T, T, F, F. Right? Okay, now I compute these, okay? And I've just got to realize compute according to the structure, right? That is the column I'll be looking at, but I can't compute that straight away. I need to know if P, what am I negating? I'm negating, right? The hand rule, right hand rule. I negate the first legal formula I come across as I uncover the symbols. Open brackets, that means I don't have a legal formula until I close the brackets. P dot Q, close brackets, that's where I've got my first legal formula. So I'm negating P and Q. Hopefully that's boring to many of you. Hopefully you're very familiar with doing that. I'm just saying it again for those who are behind. Okay, so I compute P and Q, right? And I'm going to have this column under the dot, right? And it's just T, F, F, F. That is the truth table for the dot. It's only true when they're both true. So true and true is true. A false, false is here. That makes that false. So true, false, or false. That's what I'm negating. So I look to this and I think the negation of that. So not T is false. Not false is true. Not false is true. Not false is true. That is the column that's the column for this formula, right? So what is it? A contingency or a tautology or contradiction? Just asking a different question. This statement is actually a contingency because there exist truths and there's at least one T value, there's at least one F value. Okay? Okay, so we do the second one. What do we have to do here? We have to do this last. That's the major operator. So it's a disjunction of not P and not Q. So first I have to do not P, false, false, true, true. Just looking at P and negating that. Not Q is the opposite of true, false, true, false. So false, true, true. Right? And now this, right, is the disjunction of these two. So false or false is false. What? Yes. Okay. False or false is false. False or true is true. True or false is true. True or true is true. So we've got false, true, true, true there. We've got false, true, true, true there. Those columns are identical. These two formulas are logically equivalent. All right, the columns are identical. I got confused there for a second because I was looking at the wrong thing. I was looking here. That's why maybe you put this in a different color or make sure you've got your eyes on the right place, right? It's this column you're testing against this column, right? Plenty of opportunities for confusion and mistakes by looking here or here or here. You've got to have your eyes in the right place. You're testing that one and that one. So the definition, see how that's an application of the definition. Two formulas are logically equivalent if the columns under the major operator in their joint truth table are identical, as they are. False, true, true, true in both circumstances. This particular logical equivalence, by the way, is going to be the rule of De Morgan's, or at least one of two forms of De Morgan's. You will find these two formulas separated by two pairs of double dots on the inside cover of your book under the rule De Morgan's, which you'll abbreviate DM, and you'll be using as a rule in all the proofs in units 8 and beyond. Okay, so that is a logical equivalence. You'll be getting familiar with that.